we pass a beam of light into a prism or a triangular shaped piece of glass, then the light will be refracted. And it is a principle that different wavelengths refract a different amount. For example, if this is white light comprised of all colors, the red will be bent more, and the blue will be bent least, and the green will be bent somewhere in between. So if we want to know what wavelengths are present in a beam of light, all we have to do is pass it through a prism and then capture the light on a piece of paper and see what wavelengths are present on the piece of paper. This process is known as spectrum analysis. Because we break the light into the beam into the spectrum of its different wavelengths to see what is there. Now, if we start with a simple black body radiation, which is containing all wavelengths, because that's the nature of black body radiation, and this is a beam of black body radiation, then the first thing that we can find from it is if we pass it through a prism, then we get all of the different colors spread out onto a photographic plate, and we can take a photographic plate of it, and what we can do is determine which color has the maximum intensity, which color is the most intense on our photographic plate. And we can use the relationship that lambda max times the temperature of the object is 2.9 times 10 to the 6th. The temperature is in degrees Kelvin, and the wavelength is in nanometers, and that will give us the surface temperature of the black body radiation. However, when we pass light beams through our prism, we don't always find that all of the wavelengths are present. Sometimes we find that all of the wavelengths are present, except a few are missing. They're just not there. It looks like black body radiation, but some of the wavelengths have been taken out of it. Then on another object, we will find that only certain wavelengths are there. And the profile of their intensities sort of follows a black body curve, but 90% of the wavelengths are missing, and only a few of the wavelengths are actually there. So these puzzles have to be answered as to why we have a source that's emitting black body radiation, and some of the wavelengths have disappeared or been taken out of it, and how if we study another object, we don't see black body radiation at all, but we only see wavelengths at certain discrete intervals. And the answer to that is the way that light interacts with atoms. An atom consists of a nucleus, and let's say that it has electrons that go in various orbits around the nucleus. Now, these electrons are in their normal configuration. That is, they are in the orbits that we call their ground states, the ones that they like to be in. However, these electrons, which travel around in these orbits, interact with light. And if we have light coming in, then this electron can be absorbing the light, and it can move out to a higher orbit because it now has more energy, the energy that it absorbed from the light. So it goes out to a high orbit, and it has now become excited. But that means that the light is no longer there. So these atoms are absorbing lights as long as the light is of exactly the right frequency or wavelength that it needs to go to a higher orbit, because it cannot just go to any location higher. There are only specified intervals that it can jump into. So if the incoming light has just the right amount of energy or wavelength or frequency to cause it to jump to a higher permitted orbit, then it will absorb the light and jump to that orbit. And if this happens indeed, we say why we have some of these missing wavelengths. Because what we had was a black body radiator that irradiated all wavelengths. And then it passed through some kind of cloud. And the cloud had some atoms in it that absorbed some of the wavelengths, so that the wavelengths that came out of the other side of the cloud were missing the wavelengths that got absorbed in the cloud. They were absorbed. So this is called an absorption spectra because it passed through a cloud which absorbed some of the wavelengths out of the original black body radiation. Now, by looking at the exact wavelengths that were absorbed, we can identify which of our elements did the absorbing. So we can do a chemical analysis of the cloud by seeing which of the wavelengths have been emitted. Now, in another scenario, we can have a cloud which is not emitting black body radiation, but it is having an energy input into that cloud from some other source, such as collision with some other cloud, for example, so that the atoms in this cloud are getting excited. Now, when an atom has a collision with another atom, then the energy of the collision can be used to move some of the electrons into one of their higher orbits. But since the higher orbit is not a stable or permanent location for that electron, after it sits up there for some amount of time, it will fall back into its ground state, and it will emit a piece of light, which is the energy difference between the two orbits out. So the frequency or wavelength of the light that it emits is the energy that it loses as it drops down into the lower level. So this is different for different atoms. So if we have a cloud that is not emitting thermal radiation, but is accepting energy from some other source, then this energy can be used to excite the electrons in those atoms into their higher orbits. But they're not stable there, that's not their ground state, so after some short time they will fall back to their ground state and they will emit that energy as a light wave. Now the frequency or wavelength of the light is characteristic of the atom. So we come back to our second diagram, which is an object that is only emitting certain frequencies. This is a cloud that got excited in some other way, and the electrons in the atoms got excited, moved to higher orbits, then they fell back to their ground orbits, and each time an electron falls back, it emits a wavelength that is characteristics of the energy difference between those two. So this is known as an emission spectrum. This indeed is the way that our fluorescent lights work. They work by passing an electrical signal through the gas in the fluorescent tube. This electrical signal serves to excite the particles that are in the gas into motion. As they are excited into motion and bump into each other, the electrons move into higher orbits. And as those electrons decay back into the ground state, then they emit light of certain characteristic wavelengths. Now the chemicals in the gas are very carefully chosen so that those emitted wavelengths are the ones that we want to use for visible light. Now an incandescent light bulb, the old type, does not work on this emission principle. It works on the black body principle. What it does is have a thin wire through which electric current is passed, and the electric current causes the electrons in the thin wire to move. And as they move, they cause friction with the solid part of the wire that doesn't move, and this friction heats the wire. And as the wire heats, it starts to emit black body radiation. Now, we choose that material, tungsten, such that it will heat to the right temperature where most of its emission is in the visible light that we can use. But unfortunately, a lot of the emission, because it's in black body form, is also in the infrared, which comes off as light or as electromagnetic radiation that we cannot use. So this is why incandescent old-style bulbs feel a lot hotter to our hand than fluorescent, because they are emitting infrared radiation as well as the visible light. But our fluorescent lights are very efficient. They're just emitting light in the visible region.